Okay, so in the last lecture, we have covered how to visualize Google sensing data and especially vector data, do the filtering, do the selection, select by attribute, select by location, and we also cover some of the tools that we can utilize to enhance the visualization. So for today, we're going to continue with some of the tools that we have used. Again, I need to go back to the beginning to import Google Sensing and also GMap. And then I'm going to skip to directly to color bar. So most of the tools, some of the additional tools we're going to cover here are very much similar to leaf map, okay? So we have cover leaf map. By now, you should understand like what this one is doing, right? So we are loading Google Sensing data. The only thing is different is this one. So add color bar. In GMap, I think in leaf map, it's called add color map, but they are very much similar. So look at this one here, the visualization parameters. So for this function, all we need is just passing this here minimum, maximum, and then the color palette, and then you can add a color bar. So the color bar is basically depends on this dictionary. So the minimum, the maximum, if you come here, look at this one, right? The minimum is 0, maximum is 4000, and also the color bar. So you can change it. For this line of code, you don't need to change anything unless you want to change, for example, the label and also the layer name. The label basically is the one here at the bottom, elevation. The layer name is useful because if you don't provide the layer name, then the color bar will be there all the time. If you provide the layer name, it's going to tie to that layer. So if I turn the layer off, and you see the color bar is gone as well because it's tied to the layer. So if this is something we want, you want to provide the layer name. So this is the layer, right, tied to this layer. Also, you can make changes. For example, the palette here, if this is not something you like, you can change it to other color. So the common one would be, depends on this one, for example, terrain, right? I know this is DM. So pay attention. After I run this one, see? So it has been updated. So the color bar is tied to the layer and also tied to the visualization parameters. So the visualization parameter usually have a minimum, maximum, and also the color palette. So the color palette is basically from Matplotlib. So you can change to any color you like. For example, I can change it to cool warm. It will be updated. So just based on whatever you provide. So it's very easy. Yes? You can add separate color bar. So you're going to end up with two color bar. For example, here, right now I have this, right? I can have another one. For example, I can copy this. Right? And you probably need to change the new name. For example, visualization parameter 2. And then I can do terrain, right? So here, you probably want to, for example, or the add layer, you want to have another data layer. For example, visualization 2. And then DM2, for example. And similarly, the color bar. But it doesn't make sense to do this. But you might have temperature data, you might have elevation, you might have soil moisture, wind speed, whatever. You can use a separate one. So right now, I'm going to use this one, visualization 2, and then the RTM DM2. So in this case, I'm going to end up with two layers and two color bars. Right? So just like this. And in here, I can turn this one on or off. You see? So you should be able to have two if you want to, right? I can change the layer on and off. Right, pretty easy, right? So you just need to customize and use different data set, different type of data set if you want to. Okay, good question. So in terms of DM, you can also, for example, the color bar can be, by default, it's horizontal, but you can also make it vertical. So for example, this here, look at this. So now I can make this one vertical. All you need is just one line. So what I'm doing here, because I have the layer name, so the layer name is tied to the layer, and all you need to change this one, orientation. Orientation change to vertical. By default, it's horizontal. So just one line of code, you can switch, and it's still tied to the DM. So for example, you turn it off, it should be off, right? You can also make it transparent. The transparent may not work. Let me see here. Let me run this one. And then here. Yeah, the transparent doesn't work in here. It used to work. There might be some bug. Anyway, so you can check later. Next one, split panel map. So for this one, we have covered previously in leaf map. It's very much the same mdoc split map, and then you can pass in just a string from the base map layers. So right now I have these two base map layer. We can just do it easily, but you can also do it for Earth engine data. So Earth engine data, this is an image, right? And then you want to select the land cover band. So NFCD 2021 and NFCD 2001. So we have two data layers. Then you need to convert this one to a tile layer. So because this one is the original data, original Earth engine data. And if you need to visualize them, you need to get the so-called tile layer. So tile layer basically at the end turn it into a HTTP URL. Just like you're going to Google Maps and Google Earth, right? You don't actually see the original data. You are seeing the HTTP URL. So once you have that URL, you can pass that back into the split map, left layer and right layer. And so this is what it's going to look like. So right now, we have these two data layers, right? On the left side is 2001, on the right side is 2022. So for example, I'm going to zoom into Las Vegas here. You see the changes? The urban area, right? And pretty much it's a couple lines of code. You can also turn here, right? I can turn the layer on and off. So it's very easy to use. You just need to know what do I need for the applications. So what data do I need and how do I point to the data? How do I generate the tile layer? And then how do I visualize them on the map? Next one, link map. So this one, it may not work on Google Colab. Okay, so ideally, if you can create basically a grid of data layers. So here I have four, 2 by 2, right? And if I drag one of the map, it's linked to all other maps. But I think it doesn't work on Google Colab. So on Google Colab, if you drag one map, the other map status, it doesn't change. It's just an issue with Google Colab. But if you run it locally, you should be able to do that. So this is a nice way of visualizing data in different band combinations. So you're trying to figure out, for example, which map visualization is the best for highlighting the feature you want to show on the map, right? So I can zoom in here. Where is this location? Knoxville, right? So you can see the river here, Tennessee River. And if you zoom in, right, we have the football stadium here. I think this is where we are, right? This building here. And clearly, it doesn't look all the same, right? So different band combinations. Some of them are good for highlighting certain features. Of course, if you're doing vegetation, you want this one because it's the most obvious. Vegetation all appear like red color in the fourth color composite because it has high reflectance in the near infrared band. If you have high reflectance, if you have high value, you put into the red channel, you're going to look like red color. So this is why it looks like this. On the upper left corner here, this one is the natural color combination. So basically RGB. So this one looks most likely just our human eye from look at it from space. It looks like this. This one is from the thermal, like have near infrared camera that can see vegetation, high reflectance. Human cannot see that. And there's also other combination here, depending on which one you're looking for. For example, land cover, vegetation, natural color, color infrared. So the source code looks a little bit complicated, but it's not so complicated. Okay, basically you're trying to create, for example, a link map with 2 rows and 2 columns, and the height for each map, and then where you want to center, right? So this would be the location, latitude, longitude for Knoxville, the zoom level, and then the E objects. So the E objects is going to pass in a list. If you only have one item, it's going to be replicate for all the maps. But you can pass in a list with 4 items, so the data doesn't have to be the same data. So in this case, it's the same image, different visualization. But you can also pass in different image, different data, different visualization. It's up to you. It's unlimited. And also the visualization here is we have 4 visualizations. So also it's a list, right? So this is the visualization for the first data set, the same data set, different combination, different visualization parameters. And then the label position will be the upper right, right? So upper right, this will be the label. So this is how you can create a map. You can create like as many as you want, 2 by 2, 3 by 3, 2 by 3, 3 by 4. It's like a lot of options. Questions? Next one, time series inspector. So this one to see what this one is doing. So what we're trying to do here is that, for example, I want to, I have a time series of data set. I want to visualize them all at once. So imagine you're trying to visualize data for the past, let's say, 4 decades. Every year, right? So you're gonna end up with 40 years. You don't want to add 40 layers to the map, right? Because it's probably too much. So using this one, you can have the time series inspector that allows you to load data. So for the NLCD here, we have data from 2001 all the way to 2019 on the left, and also data from the same data set. So this way you can change the data layer, right? I can zoom into Las Vegas here. Okay, so similar to the split panel map. So the split panel map only has 2 data layers, right? The time series inspector allows you to change the layer for the left, change the layer for the right. So right now, right, this is 2001. So let me show you here. If I change this one to 2011, so pay attention closely. See what happened? You see it's changing? You need to look closely. See that? So you can change the layer on the right. You can do that as well. So in this case, basically we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 images, 8 time periods. And if you want to compare them side by side, you can select whatever you want. Select one from the left, select one from the right, and then you can do the comparison. So essentially, look at how many lines call. We create a map, and then we're going to point to the lane cover data. And this image collection is basically a time series. Basically inside it has 8 images. And I'm going to select the lane cover band. And the aggregation here, aggregate array. Basically for every image, it has the index. The index in this case is just the year. So you're trying to figure out, for example, in this directory, it has 8 images. Each image, the first one is the year 2011, 2001, 2004, 6, whatever. The reason why we want to get the years is we want to pass into the label, the name, so they show up here on this drop-down list. So if you want the drop-down list, you need to pass in the label so they can use the drop-down list in here. And pretty much, you can create the app like this, just a couple lines of code, super easy to use. So the collection, so the same collection to the left, and it doesn't have to be the same. So the left and right can be different data. It doesn't have to be the same data, but in this case, we're going to compare the lane cover. So we use the same data set. The next one, time slider, okay? This might look confusing. Time series inspector, time slider. So what's the differences? And let me show you this example here. So for the data set, we're going to use the MODIS data set. And MODIS data set here have daily data. So we're going to select the data from June 1st to July 1st. So basically we have 30 images. And this is how I'm going to visualize each one. Then you can just use the function add time slider, passing the image collection. So think about image collection, just a bunch of images. And then this is how I'm going to visualize that. Also, you can set a time interval. Time interval means you can play it automatically. So you're going to show the first image, wait for 2 seconds. You go to the next one until it's done. So look at the one at the bottom here. Let me hide this one. So this is the time slider. So June 1st, you can drag the slider. So pay attention, see what happened? It will change the data layer. So otherwise, if you want to visualize the data, you need to add 30 layers to the map. It's probably too much. It's going to be overwhelming, so you're going to have 30 layers. It's just too much. So if you have a lot of data you want to see, it's better to use the time slider. And it's super easy. All we need just an image collection. Just add time slider and passing the collection, how you want to visualize that, and also the time interval, and then you can slice through, right? Or you can use this button, just play. And so for every image, you're going to show once, wait for 2 seconds, and go to the next one. So it's basically iterating through the time series. Although it's not super smooth, because you need to pull the data from the server. So there might be kind of a lag, and it's not super just like animation. It's not that good, but still, you can see some, if the internet is fast enough, you should be able to see the combination. So this might be better if you want to, for example, focus on a specific area. For example, right now, look at maybe in here, and you can see the changes. I'm not sure if you can see the changes because this is just within 1 month, so you might not see major changes. But if you're trying to compare, for example, throughout the year, you have 12 images for every month, then you might see changes, for example, temperature or other stuff. So this one is for vegetation, but you can also do temperature, right? Similarly, we can create the temperature. So this one shows you the temperature within 24 hours, right? So I can drag this one through. Again, I'm not sure if you can see the changes. It's kind of a little bit minor, but pay attention to somewhere, for example, in the US. When do you see the red color a lot? The red color, right now you don't see really red color. And if you change throughout the day, right now you don't really see red color. But you towards the end, you start to see some of the dynamics. So basically, you can visualize all kind of data. If you need to visualize time series, use the time slider or use the time series inspector. So all need to just pointing to the image collection. How you want to visualize that, that's it. And then you can repeat the same process for the entire image collection. And the last one, this one might be the most useful. I'm going to show you some use case in here. All right. Where's this location? Knoxville, right? And if I ask you a question, get monthly imagery for Knoxville, Tennessee for the past 5 years. Right. So without cloud computing, what do? I want you to generate monthly imagery for a particular location using Sentinel-2. Without using Google Sensing, you probably have to go online. You need to search website and then try to find the location and then do the filtering, and then you need to download the data. But look at this one. Just with a couple lines of code, and see here, I'm going to get the data, for example, from 2019. I get all the images. I can see all the images throughout the year. Although there might be not much changes because you don't really see major changes. But if you are looking at location that has some major changes, you can certainly see a lot of, you see the cloud in here, some days might not have cloud. And you can see it covers the area. So if you're working on any area, if you need imagery, look at this, how easy it is. So what this one is doing is, okay, I want to use the Sentinel-2 harmonized collection. That one has like hundreds of millions of images in there. And then I'm going to filter by location. Filter by this point, right? So you'll be longitude, latitude. So any images intersecting this location, I'm going to select that. And after that, I only want cloud percentage less than 10%. So that means you're only getting the good quality images. So less than 10% usually is like low coverage. And then you can also filter, I only want images acquired for the summer months from June to August. So you think about here, you can filter by location, you can filter by time, you can filter by attribute. So after you do all the combination, it's going to tell you how many images this meet the criteria. So if you want, you can just type collection dot size, and let's see how many images in there. 30 images. So that means there are 30 images that meet the criteria. And this is exactly like what we are doing here. We are using 30 images to visualize the result. And this is basically the band combination, like this. 0, 4000, and then band B8, 432, 43. But I can change the combination as well. So I can change this one, for example, to 432. Then you will be natural color composition. So comma, and then B2, and see what happened. So I'm going to run this one again. You see? So I can make changes, and literally there's not much you need to change. I just change one line of code, you can get different result. And you can see this one is a little bit dark because the blue band or the optical bands has low reflectance. So if you want to make it brighter, then probably you want to change this value to a lower number, then it will be brighter. So for example, I change to maybe 3000. Does it look better now? And see how easy it is. So just a couple lines of code, takes you a couple seconds. You can get data for any location, anywhere you like, and you can visualize them. So now if I give you a task, right? I want you to look at the data maybe how about this? Washington, D.C., right? Let's look at like the White House, Capitol Hill, or whatever, right? How do you get the data for that? How many lines of code do we need to change? It's actually pretty simple. So all you need to do, I will just come here, maybe place a marker somewhere here. That's it. So then we can figure out the location. So this one would be map. Oops. So once you place a marker, you map user RI, run it, and you just grab the location here, the coordinates. So 7.7 blah blah. Control C, and I'm gonna come to here. We place this one. Okay, that's the longitude, and then do the same thing for the latitude. Control C, and then Control V, right? And after that, you can center the location. So I'm just going to copy these two. Paste it here. That's it. All you need is to change the location. So now you're gonna get the data for this. What? There's no images? Oh, 38. Okay, good catch. So 38, 38. See? And take a look, the shape is different because the satellite orbit, the result generated is different. So we can do the same thing. I can figure out how many images in there, collection doc size. Okay, so this one has 49 images. And so now I can zoom in to this location. For example, where is it? Forest Park, DC, somewhere in here. Right? Really good. So now I have all the images. And it's throughout the year, so you can look at the differences of all the data set. Isn't it nice? You don't have to download any data. So, this one is not good. Okay, the cloud cover is too much, but you can limit it to a low number, like cloud percentage 5%. Then you might remove this one. So imagine you can stream any data you like. You can filter any data you like for any location around the globe. You can watch any movie you like for free. Right? Make sense? You can stream any geospatial data, any satellite data for free. You can visualize it easily. You can take a look. And there's not really much. It's just a browser. You don't need any specialized software to do that. All you need is just open Google Colab, run a couple lines of code, and that's it. You can get any data. We haven't done really any analysis yet. It's a lot more power they can do analysis. But in terms of just looking at the data, visualize the data, Google saying it's perfect for this kind of case. So next time, if you have any project and you need to use any satellite data, go to the Earth Engine data catalog, just search like whatever satellite data you want, and then just copy the sample code and come here, visualize that. Super fun. So for example, if the example doesn't provide, for example, Python source code. So let me quickly show you here. For example, go to Google Engine, and then I think I did show you before, right? You can convert from JavaScript to Python easily, just one click. Anyway, so that's about like searching data. You can do this for any images. It can be Sentinel-2, it can be Landsat, it can be MODIS, whatever. But for this one, you do need to pay attention to the attribute because not all data sets have the same attribute. So this one, you need to look into the data. So the easiest thing you can figure out what kind of data attribute it has, it'll be like this. So you can always pointing to the entire image collection. So this one basically give you, for example, Sentinel-2 harmonized. Essentially, this would be just like, for example, you're pointing to the entire the show. For example, Breaking Bad. How many seasons? 8 seasons? 8, 6, 5 seasons? Okay. Like this is the entire Breaking Bad TV shows. And then you can figure out, okay, I just want the first season. I want the first episode. You need to filter. But in order to do that, you can look into the entire one and then you can just, okay, preview the first one. Let's see what's inside. So just type first and just run it. It will show you the first one. So at least you get some metadata, okay. Breaking Bad, the title, and this is a unique ID on Netflix. And so this is all the cast who is appear in that, and this is all the attribute. For example, how many people and then what year, blah blah, right? You can see all the attribute, and this is the one, right? Cloud pixel percentage. So that means you can use any of these attributes to filter the data. So for example, after you select, okay, this is the cast, and then I'm going to show you, for example, this is the particular character, whatever, and then you can use this one to filter. I just want, for example, Breaking Bad, there's so many episodes. I want all the episodes that, what's the name? Jesse Pinkman, like appear in that one. Then you filter this one. So every episode going to have that attribute in there. And then you can filter easily. So there's very much the very similar idea. So again, utilize the huge data catalog. So Google Sensing has right now over 100 petabyte. Okay, 100,000 terabyte. There are tons of data. So if you know how to access that, you have everything at your fingertips. It's so powerful that you can get any data you want without having to go online to download anything. So this is how you can query the data and visualize the data, especially if you're dealing with time series. Some of the tools that we have covered, time series inspector, time slider. You can do it for any location. So you can get images for any location that you like. So this is about cloud computing, visualizing the data. Next couple sections, I'm going to quickly show you how you interact the data with a local computer. So for example, you might want to export the data to your computer, or you might want to convert some data to the cloud. So why do we need to do this? Some use case will be like this. You are watching a movie on Netflix, you really like it, you want to save a copy to your computer. How are you going to do that? Or you use a cell phone, you take a very nice video, you want to share with other people around the globe. How do you upload the data to the Netflix server? And then so you can share with other people. And then you can do cloud computing. So it basically involves back and forth. And how do you share the data? Of course, there's going to be some limit. You're not going to be able to do everything what you want, right? If the high definition like movie is like 1080p, is like 10 gigabytes, you're not going to get it within 1 second, okay? Your internet speed is not going to be that fast. And also Netflix probably doesn't want you to do that, because you can take all the movie out and then just dump it into another server, then you can have another Netflix. So they have some restrictions. Same thing to Google's engine. It's easy to get the data in, but it's difficult to get the data out. But there's some ways you can do that. But you certainly need to basically go through some process. So here we're going to cover some of these examples. First example, GeoJSON to EE. So this one, call this function here, gmap GeoJSON to EE. So you can actually convert any GeoJSON. So again, I want you to make sure you understand the differences. GeoJSON, any vector data you have on the local computer is so-called the client-side object. Any data on the Google Sensing is called server-side object. They are very different, okay? In order to utilize cloud computing, you need to have server-side object. You need to have data on their server. So right now, we're basically doing the on-the-fly conversion. We are converting the data from a local computer to the data in the cloud. So this extension is just like you have a video on your cell phone. You want to share with other people and then you want to upload to the Netflix server. You can do it using this way. but it only applies to small data set, small files. If your data is more than 10 megabyte, forget about it. You cannot do that. But you can upload to the server. You can ingest the data to do the Earth Engine code editor. But for small files, you can do that just on the fly. It allows you to basically to share it right away. So the E to GeoJSON is basically allows you to convert to vector data. And once you have this one, then you can use this one to do filtering, to do visualization, to do all kind of stuff. So for example, let me show you here, right? Right now I have this data set, and this one right now, we have this so-called FC. FC right now is the feature collection, right? So once you have the feature collection, by default, for example, I don't want to do any style. Let me show you here. I just want to add this feature collection to the map. So this is basically this is the data set I have on my local computer. But now I have converted to Earth Engine object. Once it's converted, then I can use this one to inspect. For example, I can click here. You see? Oops. What happened? It just disappeared? Oh, okay, it's here. So I'm gonna click this one. Properties. Right? So you can see, for example, the property that I have. So ISO A2, ISO A3. This will also be name here, United States of America. Right? So once I have this, you can certainly do this, right? You can filter by country. So for example, I want to see country equal to FC dot filter. Okay, nice. Name China is too big, so I'm going to have a smaller one, maybe France. All right, so country. Oh, it's uppercase, okay, not lowercase. See that? So I actually filter. So now I have the country France, and I can use this one to do filtering. So if I go back to here, I can use this one directly passing here, country. Lowercase. Of course, you need to have the source code, the country above this code block. But I'm just showing you the example. Right now, I can filter the data using this country and blah, 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 blah. And probably the center of this one, I can just use m.center center object country 10, whatever. And this is going to be a whole lot more images because you are filtering by a country level. But certainly it's doable. So you can use the data that you converted locally. So if you already have some boundary, you have some ROI, and you want to use that to filter the Earth Engine data, you will need to convert that one from your local computer to the server. Otherwise, they don't talk with each other. This is probably too many images, so it's going to take some time. But the idea is that you can, if you want to interact data, they need to be on the same domain. They need to in the Google Engine Cloud. The file, GeoJSON file on a local computer cannot directly talk to Google Engine because they're different. They're from different planet. They don't have common languages. You need to put them on the same planet so that they can talk to each other. Okay, so this is not a good example because the data set might be too big. So it's going to take some time. I'm not going to show you here. But you can easily convert data to Earth Engine. So basically, you can GeoJSON to EE, shapefile to EE, GeoPandas to EE. So you can convert basically pretty much any vector data format supported by GeoPandas to Google Engine. So similarly here, I can convert country into Google Engine. I can convert a geodata frame. And because GeoPandas can read all kind of vector data sets, so you can just use something GDF to EE. You will convert it to Google Engine, and then you can add the data layer, for example, country. That's it. So this couple functions allow you to share the, only works for vector data. For raster data, it's more complicated. It doesn't really support that. But for small vector data set, if you already have the bounding box, you have the ROI, you want to use that to filter the data set on Google Engine, then you can use this one to do the conversion. So imagine you're working on ArcGIS, you have some small vector data set. Okay, I want to use this bounding box to filter the data, then use whatever GeoJSON, swap SHP to EE or GTF to EE, then convert that one to the Earth Engine feature collection. Then it can be used to filter data. Next one, how to get data out. So if you already have some data on Google Engine, you want to export the data so that you can use it in desktop.js, then you can use this one, EE to GeoJSON, EE to SHP, EE to GTF, EE to all kind of things. So there are different options in here. So you can run this one, and then, for example, this is the state of Tennessee from Google Engine, right? And I can just use this one line of code, EE to GeoJSON, and then passing the feature collection. So this feature collection right now only contains the state of Tennessee, and I can just run this one. See, it's done. So on the left side here, if you go to your file browser, you should have the Tennessee.geojson, right? So if I click, you should have this one on your computer. So this is getting data out of Google Engine. The analogy will be like, I like this movie. I want to keep a copy of this movie, a tiny small movie, okay? Not the entire high definition 4K or 8K movie. But if it's only small, only couple megabytes, you can get it very, very quickly using this way. You can also use the EE to SHP, same thing. You can generate this one, and then you can download that one as a shape file, just like here, Imagery shape file. You can also export as a geodata frame, EE to GTF. Then you can just have access to the data frame in here. If you're trying to use the data to, for example, use some other Python packages, you might want to use the data frame because you can use that to do computation. But if you just want to export the data, then EE to GTF might be useful. And I can also use the EE to explore. Again, I want you to really understand the differences, okay? Here, GTF to explore, right now the data is on a local computer. So this is already client-side object. That's why you can use this one. But you cannot use this one, for example, the feature collection. This one here, anything that derived from the EE doc something, you cannot use GeoPandas to process that, because you can think about that one as a black box. Only Google Engine can understand that. And the file, the feature collection can be pretty big. So you cannot just use other packages to do that. For example, here, AFC, right? This is a feature collection. You cannot just say if AFC.explore, it's not going to work. Because only after you get the data out, convert that one to a GeoJSON or geodata frame, then you can use this one to explore, because this is a Python, a GeoPandas package functionality. But don't do this. It's not going to work. You see, feature collection has no attribute explore, because that one is a client-side object. Understand? They are two very different worlds. They don't talk to each other. Unless you say, please open the box, let's take a look at what's inside. You come out. But once it's open, it's exposed. You cannot go back. There's no way going back. Once it's open, it's coming to your client side. Once it's downloaded it, you are outside the cloud. You're no longer in the cloud, then you cannot utilize cloud computing. So you need to be careful about when to get the data out. Usually you want to wait until you finish all the data processing, and then you get the data out. Okay, I'm going to save a copy. But if you still want to watch it, don't get it out, because there's no way back. You can convert it back to the cloud, but you're going to only allow like small data set. You can also use EE to DF. EE to DF means you don't need the geometry. You don't need the coordinates. So for this one here, you will see you have the geometry, and that's why you can use the GTF.explore. If you don't need the geometry, then you can just EE to DF. You just need the attribute table. And this can be useful if your data set is pretty big. The boundary is very complicated. It takes a lot of space. Then you use this one to get the small data set, just the attribute table. So the attribute table sometimes can be a little bit small, so it's easy to get the data out. Lastly, you can convert this one to a CSV. So for example, I can export this one Is it Indiana? Well, actually, it's Tennessee. So this is the typo. So for example, I can export this one as a CSV. So now I should have this one here, CSV. Again, this is just typo. So you can get the data out. You can open that one as a CSV. Any questions? So easy, right? Getting data in, getting data out, and it shows all kind of data. The next section is about visualizing raster data set. So I'm going to show you different way you can get some data. In Google Sensing, there are tons of raster data set, but you don't necessarily want to download all the data. You want to utilize it to do computation, and you only extract a small subset of the data. So for this example, let me show you what it is. So for here, I have this DM, okay? So assume that right now I want to visualize the data. For example, I want to create some cross section. So here, I can use the line. I can draw a line somewhere here, for example. How about this? I draw a line across the US, and I want to see the profile. For example, the terrain, right? Because the elevation changes depends on the location. So once I have this one, I can run this center around this line here, and then we can use this function gmap.extract transect and give me the DM, give me the line, the number of segments. Basically, you're going to separate this line into 100 segments, and then the reducer, I'm going to use the mean reducer. So basically, mean elevation within each segment, and then I want to convert that one to GeoPandas. So let's see how long it takes. Okay, pretty quick, just 2 seconds. So then you get this data frame, and we can just plot it. See? Right? Easy. You can create the profile for any location, any lines. So what that one is doing is basically separate the line into 100 segments, and for each segment, it's going to calculate the mean elevation. And in Google Sensing, there's one here called reducer. Okay, this is not something like in GIS that we use. It's basically just aggregation. So for this line, right, you have the elevation here. For this line, for this segment, I'm going to take the average pixel value for this entire line, for this segment. It's called reducer. So you can use the mean reducer, you can use the median, you can use the standard deviation, you can use the sum, you can use all kind of stuff. So the reducer basically means how do you want to aggregate the data. So what we're doing is extract the transect and then use the mean elevation. So this is pretty cool. You can zoom in here, right? And you can return it back to the original one. So this one, what is showing here is the elevation changes of this line. Coming from here, from the left to the right. 100 points. It looks very detailed, but I can change it to more. So in this case, it's only 100 points. I can change it to 1000 if you want to. So in that way, you end up with more points. So let me run this one, see how long it takes. It might take a little bit longer, but I don't expect it to be super long. It's a couple seconds. We're supposed to get it. But the more points you have, the longer it's going to take, but the more data you're going to get. So see, how many seconds? 13 seconds, not too bad. And then now we can plot this one. Let me try to copy this one so that you see the differences. See? Now it's a lot more dense, right? Compared to this one, but overall the change should be pretty much similar. So now I can zoom in here, you get a lot more points. So imagine if you need to extract some data, like some sample data along a line, or along a polygon, along anything, you can use this extract the transect, especially if you have a line, then you can do this pretty easy. After that, you can export the data. For example, transect to CSV. Then you can turn this one to a CSV, and you can open it using any editor, right? So this one has 1000 points. So this would be the index, and I think it's what's this one? The location, the latitude, longitude, or the distance, and also the elevation. So that's about the extract the transect. The next section, we're going to talk about zonal statistics. If you have taken any GIS class, what is zonal statistics? What exactly is zonal statistics? What kind of thing you can do with zonal statistics? Have you ever used the ArcGIS zonal statistics too? No? Okay. Let's talk about this. So here, I show you the DM. Okay? I also show you the US state boundaries. And right now, if I ask you the question, if you answer it correctly, I give you some extra points at the end. Which US state has the lowest mean elevation? Louisiana? Okay, we pick it out. Any other answers? Florida? It's hard, right? It's not so easy. But if I ask the opposite, which US state has the highest mean elevation? Colorado? Why? Because here, right? You see the white color, the high elevation. What are the top three? So Colorado is here. What else? Which one do you think? Maybe turn this one off. Maybe turn the DM. Wyoming. Right? It's hard to tell. It's like close. So this is exactly what zonal statistics is about. You can run the statistics. The zonal, basically, each zone, you can do something. You can calculate the statistics. And so for each polygon, for example, for each state, we can calculate what's the mean elevation for each US state. And all you need is just one line of code. And you can do that for all the countries. So think about here. It can be elevation. It can be temperature. It can be crop yield. It can be soil moisture. It can be anything. So what you need is basically a vector data set, another raster data set. And you can easily answer, okay, which US state has the highest mean elevation, lowest mean elevation. And so by now you should understand, right? This is just a DM pointing to the image. And we just add the image to the map. Also with the US state boundary. And this is how we visualize that. And look at this. How many lines of code? Essentially just one line of code. gmap.zonal stats. And so inside here, basically it's a vector data set and a raster data set. So the raster data set in this case is the DM. The vector data set is the US state boundary. And here is where you want to output the data set. And the statistical type is what do you want to calculate, right? So for each US state, you have a lot of pixels inside. So basically this is the reducer. Mean means I'm going to calculate the mean elevation within this entire state. Depends on how many pixels in there. You can also specify a scale. The DM itself is 30-meter resolution. It's going to take a lot of time to use the 30-meter resolution to compute. But I can change it to a coastal resolution. You can say, okay, I just want like 1 kilometer. It's going to speed it up because you don't need the original data set. The smaller the number, the longer time it's going to take. And whether you want to return the result as a feature collection, return FC. If you don't, it's going to actually download this CSV. So let's try it out and see how long does it take. So what it's doing is going to take this entire DM covering the US, and you're going to get all the polygons covering US, and it's going to calculate all the pixels. The mean depends on the statistical type that you use. It's going to calculate the value for each one, and it's going to show you the result. But in general, it should only take a couple seconds, but depends on how busy is the server, it might take a longer time, but this is what Google Sensing is suitable for. You see, it's done. 20 to 30 seconds. Imagine you have to download the entire DM yourself and then trying to run the computation. It's going to take you minutes before you can get the result. So now with this, I can just open the data, see this. Of course, this doesn't look very good, but we can just use here. I can show you, for example, create a new code block, and I can just see maybe gmap.csv to df, okay, and then just out DSM state. So now I have this table, right? So with this data table, then I can just look at this here, mean, right? The mean is the mean elevation for every state. So right now it's not order, but we can do like sort values, okay, by mean, okay, ascending equal to false. So that means it's descending. And let's review the result. See how many did we get right? So this is descending. So what's the top one? Colorado. So the mean elevation is above 2,000. What's the next one? Wyoming, Utah. Okay. I can do the reverse. Ascending equal to 2. Then we want to start from the lowest to the highest. So let's review which US state has the lowest mean elevation. Which one? Delaware. Make sense? Mariana Islands, Virgin Islands, Florida, Louisiana actually is like way down the list. It's not the top one, definitely. Right? So this can help you answer. You can get a precise number. So this is where zonal statistics is useful for. If you have a polygon, you have a vector data set, you have a raster data set, and you want to figure out the statistics of each polygon, each zone, right? Each polygon is like one group. Within a group, I'm going to calculate like the statistics. And you can just list this one line of code in Google Engine, super simple. And you can get the data, and then you can do the organic sorting. You can download the CSV, whatever you like. You can also do multiple bands, right? So for this one, the data set that I show you here, it's the DM only has one band, but we also have a Landsat data. So the Landsat data has multiple bands. Or you can imagine, I'm going to give you the temperature data for the entire US, monthly mean temperature for the entire US. And I want you to tell me which US state has the highest temperature in July. Which US state has the highest temperature in December? It can be maximum temperature, it can be mean temperature, it can be minimum temperature. You can decide what you want to do the statistics. So here, you can basically combine all of them all together. So if the data set has multiple bands, we can do that as well. So look at this one. Similarly here, we can combine this one to gmap.csv to TF. Okay. And so this is not really mean. I don't need to sort this one. So you get all the numbers. So take a look at this one. B1, B2, B3, 4, 5, 6, and 7. Because this is the Landsat image. It has multiple spectral bands. So you can calculate the mean elevation for each band. So basically, if your image has multiple bands, if it is a time series, you can also use the zonal statistics. It will give you the table. For example, this might be January, this February, whatever you like, right? So it depends on the name of the spectral band. So you can do that for a time series data set if you want to. Questions? Okay, next use case. Let me show you this example. This is the NLCD National Land Cover data set, okay? And so it covers the US. Similarly, we have the US state boundary. So now I'm going to ask you the question. Which US state has the largest agricultural area? So which one is the agriculture? Cultivated crops, 82. So this brown is 82. So what do you think? Which US state has the largest agricultural area? Illinois? Iowa, right? Somewhere around here, right? Near this. You can tell it from the map. But if I ask the other question, which US state has the largest forest area? And this one is a little bit tricky because you have two classes. Or I can ask which US state has the largest evergreen forest, or which US state has the largest like mixed forest or wetlands or anything. So this is where, again, zonal statistics can be used for, but it's different from the DM, right? Think about here. The DM is just a continuous number. But for this one here is like in each polygon, you're not just calculating the mean, you're calculating the area of different classes. Because if, for example, for this state, you have multiple lane covers. So what's the total area for certain data, certain lane cover type? Then you can need to use different statistics. So for this one, we use the zonal statistics by group. By group means it's lane cover, so it's going to each one is one group. So different groups, you're going to get you a different number. So this one, see how it goes. Again, this data set itself is many gigabytes, so it might take some time, but you can always reduce the resolution to make it faster. So hopefully it's not taking too long. And after that, you should get a number, absolute number for every lane cover type. Okay, it's done. 20 seconds. Not too bad. So gmap.csv to df, and then NLCD stats. All right. So take a look at this. So now we have this class 81, 71, 80, blah blah. Right. This class 82 is the cultivated crop, right? Agriculture. So I can do the same thing here, sort values. Oops. And then sort by the class 82. And then ascending equal to false. That means you're going to descending. So let's take a look. Is there any error? Or no, call class. One. All right. Which one? Iowa. All right. So this is the total area. What's the second one? Kansas, North Dakota, Illinois. Right. So this is how you can easily figure out what lane cover type, right? So you can get the number. So in terms of forest, earlier it was like 42, right? Oops. Class 42. Run it. And which one the top? Oregon, California, Montana. It makes sense because you see all the green color in here. So certainly this is something you can use to answer questions. So for your final project, maybe you can think about doing some lane cover analysis using some like global data set. For example, which country around the globe has the largest forest area? It's the same idea. You can just replace the imagery and then replace the polygon with the country polygon. You can get the answer within 20 seconds, right? This solves some real problems. So this is one example. The last one I will show you here is also zonal statistics. But earlier we used the sum. The sum means you can count all the pixels together to get the total area. But you can also calculate by percentage. So why do you want to calculate by percentage? So I can ask the same question in here. Earlier I asked you like which US state has the largest agricultural area. But I can ask the question, which US state has the largest agricultural area compared to its land area? So that means, for example, the agricultural area for this one maybe, I would say maybe 80%, and this might be 70%, whatever. But you have the largest area doesn't mean that you have the largest percentage. Make sense? Because the absolute number, it also depends on how big is your the state area, right? So if you have a huge area, even if your land the agriculture is huge, you can still have a very small percentage. So you can also use the zonal statistics, but instead of using the sum, right now using the percentage. So in that way, you can also get which right now is a number, right? So for example, 0.02, that means it's 2%, 0.5%, blah blah. So at the end up, it will be 100% for all the lane cover classes. So try to think about what kind of this can be used for, because you might have different age group, different lane cover, different things, and you can calculate the percentage. Okay, so that's all for today, and we'll continue in the next lecture.